A molecular cloud is often introduced as a cold, dense region of gas where stars are born, but that description hides more than it reveals. The word cloud itself is misleading. In everyday language, a cloud is something light, fluffy, and vaguely defined, something that drifts and changes shape without much resistance. A molecular cloud is almost the opposite. It is massive, gravitationally bound over large scales, internally structured and dynamically active. If placed next to familiar terrestrial phenomena, a molecular cloud would be closer in character to a continent-sized weather system made of smoke, dust, and ice, threaded with invisible forces and carrying enough mass to form entire stellar populations. The term cloud survives mostly for historical reasons. Early astronomers observed dark patches obscuring background stars and interpreted them as clouds of obscuring material floating in space. Even today, when we know these regions are complex astrophysical systems, the name persists. But it encourages the wrong intuition. Molecular clouds are not passive reservoirs of gas waiting quietly for something to happen. They are evolving, internally turbulent structures, constantly reshaped by gravity, motion, radiation, and magnetic fields. They are not uniform, not smooth, and not temporary in the way atmospheric clouds are. Many persist for tens of millions of years, cycling material through different internal phases before finally dispersing. In terms of size, molecular clouds operate on scales that challenge human intuition. Smaller examples, often called molecular cloud complexes, can span tens of light years from end to end. Larger systems, known as giant molecular clouds, routinely extend over 100 light years and sometimes several hundred. To put that in perspective, a cloud only 50 light years across is large enough to contain thousands of solar systems laid end to end. These clouds are not isolated blobs either. They often form long chains along spiral arms of galaxies, overlapping and interacting with their surroundings, merging and fragmenting as they orbit the galactic center. Their mass is even more counterintuitive. A modest molecular cloud might contain a few thousand times the mass of the Sun. Giant molecular clouds can contain millions of solar masses. This means that a single cloud can hold enough material to form entire star clusters, including massive stars that will later shape the galaxy around them. Despite this enormous mass, the average density of a molecular cloud is still far lower than anything we experience on Earth. Even in relatively dense regions, there may be only a few hundred to a few thousand particles per cubic centimetre. By laboratory standards, this is an extreme vacuum. What makes the cloud massive is not density, but volume. Spread that tenuous gas over hundreds of light years, and gravity begins to matter. The composition of a molecular cloud is deceptively simple at first glance, but subtle in its implications. The dominant component by far is molecular hydrogen, H2. It accounts for the majority of the mass, yet it is almost completely invisible under the conditions found in these clouds. Molecular hydrogen does not emit strongly at the low temperatures typical of molecular clouds, which are often around 10 Kelvin, roughly minus 263 degrees Celsius, or minus 441 degrees Fahrenheit. As a result, astronomers cannot usually observe H2 directly. This creates a paradox. The most important ingredient is the hardest to see. To work around this, astronomers rely on tracer molecules, the most important of which is carbon monoxide. Although carbon monoxide is far less abundant than molecular hydrogen, it emits radiation at millimetre wavelengths that can be detected with radio telescopes. By mapping carbon monoxide emission, astronomers infer the presence, motion, and approximate amount of molecular hydrogen. This method is indirect and imperfect, but it has revealed the large-scale structure of molecular clouds throughout galaxies. Variations in carbon monoxide emission often trace filaments, clumps, and velocity gradients that hint at deeper processes occurring within the cloud. Dust grains, though they make up only about 1% of the cloud's mass, play an outsized role. These microscopic particles, composed of silicates, carbon compounds and ices, act as both shields and catalysts. Dust absorbs and scatters ultraviolet and visible light from nearby stars, protecting the interior of the cloud from radiation that would otherwise heat and dissociate molecules. This shielding allows molecular hydrogen to survive and accumulate. Dust grains also provide surfaces on which hydrogen atoms can meet and bond, forming H2 more efficiently than in the gas phase alone. Thermally, dust is crucial because it enables cooling. Dust grains emit infrared radiation, allowing the cloud to lose energy without dramatic motion. This cooling keeps temperatures low, which in turn keeps gas pressure low. Low pressure is one of the prerequisites for gravitational collapse. In this sense, dust grains quietly prepare the conditions for star formation long before any star actually forms. The reason molecular clouds appear dark is directly tied to this dust. In optical wavelengths, dust blocks background starlight, creating the appearance of black voids against the star-rich backdrop of a galaxy. These dark regions were among the first clues that dense interstellar structures existed at all, but darkness is only part of the story. Molecular clouds are also cold, far colder than the surrounding interstellar medium. Atomic gas elsewhere in the galaxy often sits at temperatures of thousands of degrees, while molecular clouds remain near the lowest temperatures achievable without external heating. This coldness is not accidental. It is maintained by the balance of radiative cooling, dust shielding, and limited energy input from the environment. Structurally, molecular clouds are anything but uniform. High-resolution observations reveal a nested hierarchy of features. On the largest scales, clouds often organize into elongated filaments stretching tens of light years. These filaments can intersect, braid, and branch, forming networks that resemble cosmic infrastructure more than amorphous fog. Within filaments, denser clumps appear, regions where gas density is higher and motions are slower. Within clumps, still denser cores emerge, compact regions that may eventually collapse into stars. This hierarchy is not simply a matter of scale, it reflects underlying physical processes. Filaments often arise from large-scale flows and shocks in the interstellar medium. Supersonic motions compress gas along preferred directions, especially when guided by magnetic fields. Clumps form where filaments intersect, or where turbulent compression briefly overwhelms pressure support. Cores represent the densest, coldest pockets, where gravity begins to dominate locally, even if the cloud as a whole remains supported. One of the defining properties of molecular clouds, and one of the most counterintuitive, is turbulence. In everyday contexts, turbulence is associated with chaos, noise, and instability. In molecular clouds, turbulence is a fundamental organizing feature. Gas within these clouds moves at speeds that often exceed the local speed of sound, making the turbulence supersonic. This motion creates shocks, density fluctuations, and complex velocity fields that shape the cloud on all scales. Turbulence in a molecular cloud is not a small correction to an otherwise calm system. It dominates the internal dynamics. Observations show broad spectral lines, indicating that gas parcels within the same region move at different velocities. This motion provides an effective pressure that can counteract gravity on large scales, preventing the entire cloud from collapsing at once. At the same time, turbulence creates localized compressions where gas density increases dramatically. In these compressed regions, gravity can take over, leading to the formation of dense cores. This dual role makes turbulence both a stabilizing and destabilizing influence. It delays global collapse while seeding local collapse. Importantly, turbulence is not eternal. Without continuous energy input, turbulent motions decay over time, typically on timescales comparable to the crossing time of the cloud. This means that molecular clouds must be constantly stirred by external forces such as galactic shear, spiral arm passage, or nearby stellar activity. When that stirring weakens, the balance shifts. The presence of turbulence also means that molecular clouds are never truly in equilibrium in the strict sense. While they may appear roughly stable when averaged over large regions, internally they are in constant flux. Filaments accrete material, clumps merge or disperse, and velocity fields evolve. What looks like a static dark patch in the sky is, in reality, a slow, complex dance of matter responding to gravity and motion. Another reason molecular clouds are structurally complex is that gravity operates differently across scales. On the largest scales, the cloud's self-gravity competes with turbulent pressure and magnetic support. On smaller scales, gravity becomes increasingly important as density rises and temperature remains low. This scale-dependent behavior ensures that different regions of the same cloud can be at very different evolutionary stages simultaneously. Some parts may be forming stars, others may be dispersing, and still others may remain quiescent for millions of years. This complexity is compounded by the fact that molecular clouds are not closed systems. They exchange mass and energy with their surroundings. Gas flows into them from the diffuse interstellar medium and flows out through evaporation, ionization, or mechanical feedback from young stars. Radiation penetrates their outer layers, altering chemistry and temperature gradients. Magnetic fields thread through them, linking their internal dynamics to the larger galactic environment. In this sense, a molecular cloud is less like an isolated object and more like a node in a galactic ecosystem. Understanding what a molecular cloud actually is requires abandoning simple metaphors. It is not a static container, not a uniform medium, and not merely a prelude to star formation. It is an active, evolving structure whose properties emerge from the interplay of gravity, motion, radiation, and chemistry. Its darkness is not emptiness, but shielding. Its coldness is not inactivity, but preparation. Its turbulence is not disorder, but structure in motion. When viewed this way, the molecular cloud becomes the true starting point of stellar evolution, not because stars immediately form within it, but because it establishes the physical conditions under which star formation becomes possible at all. Long before the first core collapses or the first protostar ignites, the cloud has already done most of the work, quietly assembling mass, dissipating energy, and organizing matter on scales vast enough to shape the future of a galaxy. Molecular clouds do not appear suddenly, and they are not the default state of interstellar matter. They are the end result of a long, inefficient, and highly selective process that operates on galactic scales. Most of the gas in a galaxy never becomes molecular, and even less of it ever participates in star formation. To understand how molecular clouds form in the first place, it is necessary to step back from the cloud itself and look at the large-scale environment of a galaxy where gravity, rotation, shock waves, and radiation constantly reshape the interstellar medium. Galactic disks are filled primarily with atomic hydrogen rather than molecular hydrogen. This atomic gas is warm compared to molecular clouds, typically hundreds to thousands of Kelvin, and it is diffuse with relatively low densities. Left alone, this gas would remain atomic and spread out. Something has to compress it, cool it, and protect it from radiation before molecules can form in large quantities. That something is not a single mechanism, but a combination of large-scale drivers that act together over long periods of time. One of the most important drivers is spiral arm compression. In disk galaxies with spiral structure, spiral arms are not rigid objects, but density waves that move through the disk. As gas orbits the galactic center, it encounters these spiral density enhancements. When atomic gas flows into a spiral arm, it slows down relative to the pattern, compressing as it piles up. This compression increases the gas density and triggers cooling. Over tens of millions of years, repeated passage through spiral arms can gradually transform diffuse atomic gas into denser structures that are more conducive to molecule formation. Spiral arm compression is not a violent process. It does not produce explosions or sharp boundaries. Instead, it is more like traffic congestion on a galactic scale. Gas enters a crowded region, slows, compresses, and lingers. During this time, radiative cooling becomes more effective, temperatures drop, and densities rise. These conditions favour the formation of molecular hydrogen, provided that the gas can be sufficiently shielded from ultraviolet radiation. Spiral arms therefore act as assembly lines, concentrating material and giving it time to evolve chemically and thermally. Gravitational instabilities provide another large-scale pathway to cloud formation. Galactic disks are not perfectly stable systems. Under certain conditions, regions of the disk can become gravitationally unstable, meaning that self-gravity overcomes pressure and rotational support. When this happens, gas can clump together over large areas, forming massive complexes that later fragment into molecular clouds. These instabilities depend on factors such as gas surface density, rotation speed, and temperature, and they vary from galaxy to galaxy. In regions where gravitational instabilities dominate, molecular clouds can form even in the absence of well-defined spiral arms. The disk itself becomes prone to collapse on large scales, creating vast, irregular gas structures. These structures may later shear apart due to differential rotation, but during their lifetime, they can reach densities high enough for molecular chemistry to take hold. This mechanism is particularly important in galaxies with weak or flocculent spiral structure, where spiral arm compression alone cannot account for observed cloud populations. Converging gas flows are another critical ingredient. The interstellar medium is not static. It is constantly stirred by stellar feedback, galactic rotation, and large-scale motions. Supersonic flows of atomic gas can collide, compressing material at their interface. Where these flows converge, gas density increases rapidly and cooling becomes efficient. These converging flows can be driven by many sources, including expanding shells from previous star formation, large-scale turbulence in the galactic disk, or shear between different orbital streams. Unlike spiral arm compression, which acts over long distances and timescales, converging flows can create dense regions relatively quickly on local scales. However, the resulting structures are often transient, unless supported by gravity or reinforced by additional compression. Many such compressed regions dissipate before becoming fully molecular. This contributes to the inefficiency of molecular cloud formation. Compression alone is not enough. The gas must remain dense and shielded for long enough that molecules can form and survive. Supernova shock waves play a complex and often misunderstood role in this process. Supernova inject enormous amounts of energy into the interstellar medium, driving expanding shock fronts that sweep up surrounding gas. These shocks can compress atomic gas to higher densities, potentially triggering cooling and molecule formation in their wake. In this sense, supernovae can contribute to the creation of molecular clouds by providing strong, localized compression. At the same time, supernovae are also destructive. The same shocks that compress gas can heat it, ionize it, and disrupt existing molecular structures. Whether a supernova promotes or inhibits molecular cloud formation depends on timing, environment, and geometry. A shock moving into diffuse atomic gas can help initiate cloud formation, while a shock impacting an already formed molecular cloud may tear it apart. Over galactic timescales, supernovae act less like builders or destroyers and more like recyclers, constantly reshaping the medium and redistributing energy and matter. The transition from atomic hydrogen to molecular hydrogen is a central step in cloud formation, and it is far from automatic. Atomic hydrogen dominates in environments exposed to ultraviolet radiation, which easily dissociates molecular hydrogen. To form and maintain H2, the gas must be both dense enough for molecules to form efficiently and shielded enough to prevent their destruction. This is where dust and self-shielding become essential. Molecular hydrogen forms primarily on the surfaces of dust grains. In the gas phase, the formation of H2 is extremely inefficient under typical interstellar conditions. Dust grains provide sites where hydrogen atoms can stick, meet, and bond before being released back into the gas as molecules. Without dust, molecular clouds, as we know them, would not exist. The abundance of dust therefore directly influences the ability of a galaxy to form molecular gas and, by extension, stars. Once some molecular hydrogen has formed, it begins to protect itself through self-shielding. H2 absorbs ultraviolet radiation at specific wavelengths. As the column density of molecular hydrogen increases, these absorption lines become saturated, preventing radiation from penetrating deeper into the cloud. This allows molecular hydrogen to survive in the interior, even if the outer layers are exposed to radiation. Self-shielding is not perfect, but it significantly reduces the destruction rate of molecules once a critical density is reached. Dust shielding works alongside self-shielding. Dust grains absorb and scatter ultraviolet photons across a broad range of wavelengths, reducing the radiation field inside dense regions. This shielding is especially important for protecting other molecules such as carbon monoxide, which are more easily destroyed than H2. Together, dust shielding and self-shielding create chemically distinct interiors where molecular chemistry can proceed. Despite these mechanisms, most gas in a galaxy never becomes molecular. The reasons are both physical and environmental. Much of the gas remains too diffuse for efficient molecule formation. In low-density regions, hydrogen atoms rarely encounter dust grains, and any molecules that do form are quickly destroyed by radiation. In addition, large volumes of gas reside in environments with strong ultraviolet fields, such as near massive stars, where shielding is insufficient. Metallicity also plays a role. Dust grains are made from heavy elements, so galaxies with lower metallicity have less dust. In such environments, molecule formation is less efficient, and molecular clouds are harder to assemble. This is why star formation behaves differently in metal-poor galaxies and in the early universe. The absence of abundant dust raises the threshold for molecular cloud formation, making the process even more selective. Time is another limiting factor. Even under favourable conditions, the assembly of a molecular cloud takes a long time. Gas must be gathered, compressed, cooled, and chemically transformed. These processes operate on timescales of tens of millions of years. During that time, the galactic environment does not stand still. Gas flows continue, radiation fields change, and disruptive events occur. Many potential clouds are interrupted before they can fully form. This long timescale explains why molecular clouds are relatively rare compared to the total amount of gas in a galaxy. It also explains why star formation is slow and inefficient on galactic scales. Only a small fraction of gas ever reaches the conditions required for molecular cloud formation, and only a fraction of that molecular gas goes on to form stars. The rest is recycled back into the diffuse interstellar medium through feedback and dispersal. Importantly, molecular cloud formation is not a single universal pathway. Different regions of a galaxy may rely on different combinations of mechanisms. Spiral arms may dominate in one area, while converging flows or gravitational instabilities dominate in another. Supernovae may help assemble clouds in one epoch and destroy them in another. The result is a population of molecular clouds with diverse histories, structures, and lifetimes. What unifies these pathways is their quietness. There is no single moment when a molecular cloud is born. Instead, there is a gradual shift in physical conditions, a slow accumulation of mass, and a progressive change in chemistry. By the time a region is clearly identifiable as a molecular cloud, much of the work has already been done invisibly. The gas has cooled, shielding has built up, and molecules have formed in sufficient numbers to dominate the mass. In this sense, molecular cloud formation is a process of subtraction as much as addition. Energy is radiated away. Motion is damped. Radiation is blocked. What remains is cold, dense, molecular gas embedded in a much larger, more active galactic environment. This quiet preparation sets the stage for everything that follows, but it unfolds on timescales so long and in ways so subtle that it leaves almost no direct observational signature. By the time stars begin to form, the decisive steps occurred tens of millions of years earlier, in a slow, patient transformation of atomic gas into something far rarer and far more consequential. Molecular clouds are often described as calm, cold, and long-lived, and from an observational standpoint, this description seems justified. When astronomers map these regions, they frequently see vast structures that persist over millions of years, showing no obvious signs of rapid collapse or violent motion. Compared to supernova remnants, stellar winds, or ionized nebulae, molecular clouds look quiet. This apparent calmness has led to the intuitive idea that molecular clouds are stable objects, balanced delicately against gravity and waiting passively for star formation to begin. That intuition, however, is deeply misleading. The calm appearance of a molecular cloud is not evidence of true stability. It is the result of several competing forms of support, operating simultaneously and unevenly, combined with severe observational limitations. Molecular clouds are not static equilibria. They are metastable systems, temporarily resisting collapse while slowly evolving internally. The illusion of stability arises because the forces that oppose gravity do not eliminate motion or change. They redistribute it in ways that are difficult to see. The most basic form of support against gravity is thermal pressure. In any gas, temperature corresponds to the random motion of particles. Higher temperatures mean faster motions and higher pressure, which resists compression. In molecular clouds, temperatures are extremely low, typically around 10 Kelvin. At such temperatures, thermal pressure alone is very weak. If molecular clouds were supported only by thermal pressure, they would collapse rapidly under their own gravity on timescales much shorter than what is observed. This immediately tells us something important. Thermal pressure cannot be the dominant source of support in most molecular clouds. The internal motions required to counteract gravity must come from somewhere else. That somewhere else is turbulence. Gas inside molecular clouds does not sit still. It moves chaotically, with velocities that often exceed the local speed of sound. These motions contribute an effective pressure, sometimes called turbulent pressure, which acts in a way similar to thermal pressure but arises from bulk motion rather than microscopic agitation. Turbulent pressure is scale-dependent. On large scales, turbulent motions can be strong enough to counteract gravity across an entire cloud or cloud complex. On smaller scales, turbulence becomes less effective. Energy cascades from large scales to smaller ones, eventually dissipating as heat. As a result, turbulence can support a cloud globally while failing to prevent local collapse in dense regions. This uneven distribution of support is a key reason why clouds appear stable overall while still forming stars internally. The presence of turbulence also complicates the interpretation of motion. When astronomers measure velocity dispersion in a cloud, they often find broad spectral lines, indicating a wide range of velocities along the line of sight. This is sometimes interpreted as evidence of equilibrium, with turbulent pressure balancing gravity. But turbulence is not a static force. It decays over time unless continuously replenished. The fact that turbulence exists does not guarantee long-term stability. It only delays collapse. Magnetic fields add another layer of apparent stability. Interstellar magnetic fields thread through molecular clouds, coupling charged particles to field lines and influencing the motion of a neutral gas through collisions. Even relatively weak magnetic fields can have significant dynamical effects when acting over large volumes. Magnetic pressure and magnetic tension both contribute to resisting gravitational compression, particularly in directions perpendicular to the field lines. Magnetic support is often invoked to explain why some regions of molecular clouds do not collapse despite being dense and cold. Field lines can act like elastic bands, resisting compression and channeling motion along preferred directions. This leads to anisotropic collapse, where gas flows more easily along magnetic field lines than across them. As a result, clouds can maintain elongated or filamentary shapes while still evolving internally. However, magnetic fields do not freeze molecular clouds in place. Over time, neutral gas can drift relative to the magnetic field through a process known as ambipolar diffusion. This allows gravity to gradually overcome magnetic support in dense regions. The timescale for this process can be long, contributing to the extended lifetimes of clouds, but it does not prevent collapse indefinitely. Magnetic fields delay collapse. They do not stop it. One of the most commonly cited concepts in discussions of cloud stability is virial equilibrium. In its simplest form, virial equilibrium describes a balance between kinetic energy and gravitational potential energy in a bound system. If these energies are in the right proportion, the system neither collapses nor expands rapidly. Many molecular clouds appear at first glance to satisfy this condition when their observed masses and velocity dispersions are plugged into the virial framework. This has led to the widespread idea that molecular clouds are virialized objects, hovering in a stable equilibrium state. The problem is not with the virial theorem itself, but with how it is applied. The virial theorem is a statement about time-averaged properties of a system, not a guarantee of instantaneous or permanent balance. A cloud can appear virialized at a given moment, while still evolving toward collapse or dispersal. Moreover, the virial analysis often neglects important factors. External pressure from the surrounding interstellar medium, magnetic energy, surface terms, and time-dependent flows all complicate the picture. Observed velocity dispersions may reflect large-scale inflows, outflows, or transient motions rather than true internal support. In some cases, what looks like turbulent support may actually be gas already responding to gravity. This misunderstanding of virial equilibrium contributes significantly to the illusion of stability. When clouds are labelled virialized, it suggests a long-lived balance that may not exist. In reality, many molecular clouds are better described as marginally bound or marginally unstable systems, constantly adjusting to changing internal and external conditions. Another reason collapse does not begin everywhere at once is the inherently inhomogeneous nature of molecular clouds. Density is not uniform, temperature is not uniform, magnetic field strength is not uniform, turbulent energy is not uniform. Gravity responds to these variations. Regions that are slightly denser or slightly cooler than their surroundings experience stronger gravitational attraction and weaker pressure support. Collapse begins in these pockets first. This local collapse does not immediately disrupt the rest of the cloud. On large scales, the cloud can remain supported while small regions undergo contraction. From the outside, the cloud still looks calm. Internally, it is quietly fragmenting. This hierarchical behavior is a fundamental feature of molecular cloud evolution. Global stability and local instability are not contradictions, they are two sides of the same process. Observational bias reinforces the impression of calmness. Most of what we know about molecular clouds comes from traces that are sensitive to particular densities, temperatures, or chemical compositions. These traces often highlight the bulk of the cloud rather than its most dynamic regions. Dense cores, where collapse is most advanced, occupy only a small fraction of the cloud's volume and mass. They are easy to miss unless specifically targeted. In addition, many of the motions associated with early collapse are subsonic or mildly supersonic. They do not produce strong shocks or bright emission. Gas can flow inward at a few tenths of a kilometre per second, radiating energy away efficiently. Such motions are difficult to distinguish from turbulent background motion, especially when observations are limited by resolution and sensitivity. Projection effects further obscure dynamics. Observations collapse three-dimensional structures into two-dimensional maps and line-of-sight velocities. Complex flows can cancel out or appear static when averaged along the line of sight. A region that is actively accreting material from multiple directions may look quiescent in projection, reinforcing the impression of stability. Timescale also plays a role in shaping perception. Human intuition is tuned to short timescales. A structure that changes significantly over millions of years appears static to us. Molecular clouds evolve slowly compared to explosive astrophysical phenomena, but slow does not mean stable. The absence of rapid change is mistaken for equilibrium, when it is often simply the result of gradual evolution. All of these factors contribute to the idea that molecular clouds are stable objects, when in fact they are metastable. A metastable system is one that persists in a configuration that is not the lowest possible energy state, protected by barriers that delay transition. Molecular clouds fit this description well. Gravity is always trying to pull them inward toward collapse. Various forms of support slow this process, creating a long-lived intermediate state. This metastability is not uniform across the cloud. Different regions sit at different distances from instability. Some may remain supported for tens of millions of years. Others may cross the threshold into collapse relatively quickly. The cloud as a whole does not switch abruptly from stable to unstable. It continuously explores a range of states, with local collapses gradually altering the global balance. Crucially, metastability means that small changes can have large effects. A slight increase in density, a modest loss of turbulent energy, or a gradual weakening of magnetic support can tip a region into collapse. These changes need not be dramatic or externally triggered. They can arise naturally from the cloud's internal evolution. From the outside, nothing obvious happens. From the inside, gravity gains ground. The illusion of stability is therefore a product of perspective. From afar, molecular clouds look calm because their most important processes are subtle, slow, and deeply embedded. From within, they are dynamic environments, constantly reshaped by competing forces. The apparent calm is not a sign of inactivity, but of balance in motion. Understanding this illusion is essential for understanding star formation itself. Stars do not form because a stable cloud suddenly becomes unstable everywhere. They form because metastable systems inevitably evolve, and local regions cross thresholds at different times. The quietness of molecular clouds is not a mystery to be explained away. It is a natural consequence of how gravity, turbulence, magnetic fields and radiation interact over vast scales and long times. In this sense, molecular clouds are calm in the same way a mountain range is calm. The mountains do not move on human timescales, yet they are the result of immense forces acting over millions of years, and they continue to erode, shift, and respond to stress. Molecular clouds, too, are shaped by forces that operate slowly but relentlessly. Their stability is temporary, their calm deceptive, and their evolution already underway long before it becomes visible. Cooling is the least dramatic process involved in the collapse of a molecular cloud, and yet it is the most decisive. Gravity cannot take control unless the gas can lose energy. Density alone is not enough. A cloud can become denser through compression and still resist collapse if its temperature remains high. What ultimately determines whether gravity gains the upper hand is not how much mass is present, but how effectively that mass can rid itself of heat. In molecular clouds, collapse is not triggered by motion or shock, but by the quiet removal of thermal energy. To understand why temperature matters more than density, it helps to recall what pressure actually is. Gas pressure arises from particle motion. Even a very tenuous gas can exert significant pressure if its particles move fast enough. Conversely, a dense gas can offer little resistance to gravity if its particles move slowly. In molecular clouds, temperatures are already low compared to most astrophysical environments, but even small changes in temperature have large consequences. Lowering the temperature by a factor of 2 halves the thermal pressure. Gravity does not need dramatic density increases if pressure is steadily drained away. This is why cooling is so powerful. It does not require gas to move inward. It does not require shocks or compression. Cooling can act in place. A parcel of gas can remain where it is while quietly losing energy to radiation. As its temperature drops, its pressure support weakens. Gravity, unchanged, suddenly finds less resistance. Collapse can begin without any visible trigger, driven not by motion but by absence. In molecular clouds, cooling is dominated not by continuum emission from hot gas, but by very specific atomic and molecular transitions. At the low temperatures involved, most atoms and molecules occupy their lowest energy states. Only a small number of transitions are available, and only certain species can radiate efficiently. Among these, carbon monoxide plays a central role. CO has a ladder of rotational transitions that can be excited at temperatures of just a few Kelvin. When collisions excite these rotational states, the molecule emits photons at millimeter wavelength as it relaxes. Each emitted photon carries energy away from the gas. Ionized carbon, often referred to as C+, is another important coolant, particularly in the outer regions of clouds and in transitional zones where gas is not fully molecular. The fine structure transition of C+ emits in the far infrared and can dominate cooling where CO is scarce or destroyed by radiation. Neutral oxygen also contributes through its own fine structure lines, especially in slightly warmer or denser regions. These cooling channels are remarkably efficient given how little material is involved. A tiny fraction of carbon or oxygen atoms can regulate the thermal state of enormous volumes of gas. The reason lies in how easily these species are excited and how effectively their emitted radiation escapes the cloud. Unlike dense stellar interiors, molecular clouds are optically thin at many infrared and millimeter wavelengths. Photons can leave without being reabsorbed, carrying energy into space. As the gas cools, its sound speed drops. This has immediate consequences for stability. The threshold mass required for gravitational collapse decreases as temperature falls. Regions that were previously supported suddenly become unstable, not because they gained mass, but because their internal motions slowed. Cooling therefore changes the gravitational landscape of the cloud, redefining which regions are vulnerable to collapse. Dust grains become increasingly important as temperatures drop. At low temperatures, gas and dust are thermally coupled through collisions. Gas particles transfer kinetic energy to dust grains, which then radiate that energy away in the infrared. This dust-gas coupling is particularly effective in dense regions where collisions are frequent. Dust grains act as thermal sinks, smoothing out temperature variations and allowing gas to cool below what molecular line emission alone could achieve. Dust emission is broadband and continuous, unlike the discrete lines of molecular cooling. At temperatures around 10 Kelvin, dust emits primarily in the far infrared and sub-millimeter range. This emission is faint, spread over large areas, and difficult to detect against background noise. Yet it represents a steady drain of energy from the cloud. Over long timescales, this quiet radiation removes vast amounts of thermal energy without producing any obvious dynamical signature. One of the most counterintuitive aspects of cooling-driven collapse is that it accelerates gravity without accelerating motion. In many physical systems, collapse is associated with rapid inflow, shocks, or turbulence. In molecular clouds, early collapse can proceed subsonically. Gas drifts inward slowly, radiating energy as it goes, never building up enough kinetic energy to produce dramatic signatures. The process is closer to settling than falling. This is possible because cooling keeps pace with compression. As gas contracts slightly under gravity, its density increases, which would normally raise temperature and pressure. Cooling counteracts this heating almost immediately, bleeding off the excess energy. The result is near isothermal contraction, where temperature remains roughly constant even as density rises. In such a regime, pressure does not increase enough to halt collapse. Gravity continues to win quietly. This near isothermal behavior is one of the defining characteristics of molecular cloud collapse. It allows fragmentation to proceed efficiently, breaking clouds into smaller and smaller structures. Each fragment can cool as it contracts, maintaining low pressure and enabling further collapse. Without efficient cooling, fragmentation would be suppressed, and star formation would look very different. Cooling also reshapes turbulence. Turbulent motions dissipate energy through shocks and shear. In a warm gas, this dissipation heats the medium, potentially increasing pressure and restoring support. In a cold, efficiently cooling gas, dissipated energy is radiated away almost immediately. Turbulence loses its ability to sustain itself. Over time, turbulent support weakens, not because motion stops instantly, but because energy is no longer retained. This gradual loss of turbulent energy is another way cooling enables collapse. Turbulence can delay gravity, but only if it is continually replenished. Cooling short-circuits this process by ensuring that any injected energy is quickly lost. In the absence of strong driving forces, turbulence decays and gravity gains influence. Again, nothing dramatic happens. No explosion marks the transition. The cloud simply becomes quieter in a physical sense, even if it still looks chaotic observationally. The silent nature of cooling-driven collapse is reinforced by how little radiation is produced. The energy released during early collapse is small compared to stellar processes, and it is emitted at wavelengths that are hard to observe. Infrared and submillimeter radiation from cold dust blends into background emission from the galaxy. Molecular line emission spreads over wide velocity ranges, making it difficult to isolate collapse signatures from general cloud motion. As a result, much of the most important energy loss in a molecular cloud goes unnoticed. Observationally, the cloud appears dark and inactive. In reality, it is constantly radiating away the energy that keeps gravity at bay. The collapse is not announced by light or motion, but by the steady absence of heat. The importance of infrared emission cannot be overstated, even though it is barely detected in many cases. Infrared photons carry information about temperature, density, and composition. They reveal where dust is cooling efficiently and where gas-dust coupling is strongest. Modern infrared observatories have begun to map cold dust emission in unprecedented detail, uncovering networks of filaments and cores that were previously invisible. These observations confirm that cooling is highly structured, concentrated in the very regions where collapse is most likely. Yet even with advanced instruments, we see only part of the picture. Some of the coldest, densest regions emit so weakly that they are detectable only indirectly through absorption or subtle spectral features. These are often the sites of future star formation, already deep into the collapse process before any protostar forms. By the time a star announces itself, cooling has already done its work. Cooling also sets the pace of collapse. Freefall times, calculated assuming no pressure support, provide an upper limit on how fast gravity can act. In practice, cooling determines whether collapse approaches this limit or proceeds more slowly. Efficient cooling allows collapse to proceed nearly at the freefall rate. Inefficient cooling stretches the process out, giving other forms of support time to intervene. In molecular clouds, cooling is efficient enough that once collapse begins locally, it is difficult to stop. This efficiency explains why star formation, once initiated in a dense core, tends to be decisive. The quiet preparation phase may take tens of millions of years, but the final stages of collapse accelerate rapidly. Cooling ensures that pressure never builds up enough to reverse the process. The silence ends only when a protostar forms and new sources of energy appear. From a broader perspective, Cooling is the bridge between large-scale galactic processes and small-scale star formation. Spiral arm compression, converging flows, and turbulence assemble and shape molecular clouds, but none of these processes guarantee collapse. Cooling is what translates structure into instability. It removes energy without removing mass, tilting the balance toward gravity. This is why cooling deserves to be seen not as a secondary effect, but as the central enabler of collapse. Without efficient cooling, molecular clouds would be transient compressions that rebound and disperse. With cooling, they become reservoirs of potential, slowly evolving towards star formation, even while appearing calm. The quietness of this process is not accidental. Nature has no need for spectacle here. The universe forms most of its structure not through explosions, but through patience. Molecular clouds cool, pressure fades, gravity tightens its grip, and collapse begins without sound, light, or warning. By the time anything dramatic happens, the decisive step has already been taken, long ago in the dark. Gravity does not overwhelm a molecular cloud all at once. There is no single threshold where an entire cloud suddenly gives way and collapses inward. Instead, gravity wins selectively, quietly, and locally through a process known as the gene's instability. Despite its central importance to star formation, this instability is often misunderstood because it is usually introduced mathematically. Stripped of equations, the underlying idea is simpler and more subtle. Gravity succeeds wherever internal support fails on the right scale. At its core, the gene's instability describes a competition between gravity and pressure. Gravity tries to pull matter together. Pressure, generated by particle motion, resists that pull. Whether a region collapses depends on which influence dominates, but crucially, the answer depends on scale. A region can be stable on one scale and unstable on another at the same time. This scale dependence is the key to understanding why molecular clouds fragment rather than collapse as a whole. Imagine a region of gas inside a molecular cloud. Gravity acts on all the mass in that region, pulling it inward. Pressure, on the other hand, acts through communication. Pressure resists collapse by transmitting forces through particle motion, effectively sending signals across the region. If pressure can respond quickly enough across the entire region, it can counter gravity. If it cannot, gravity gains the advantage. The ability of pressure to respond depends on how fast information travels through the gas, which in turn depends on temperature. This leads to the idea of a critical length. Below this length, pressure can coordinate the response of the gas efficiently. Above it, pressure cannot keep up, and gravity begins to dominate. This critical size is not fixed. It depends on temperature and density. Colder gas has slower particle motions, so pressure signals travel more slowly. As a result, the critical length shrinks. Regions that were once stable become unstable simply because the gas cooled. There is also a corresponding critical mass. A region smaller than the critical length, but containing enough mass, can still collapse. Conversely, a large region with insufficient mass may remain stable. These two concepts, critical length and critical mass, define where gravity can win. Importantly, they apply locally. Each part of a molecular cloud has its own conditions, its own thresholds, and its own fate. This is why collapse begins locally rather than globally. A giant molecular cloud may contain millions of solar masses, but it also contains turbulence, magnetic fields, and temperature variations. On the largest scales, turbulent motions and magnetic support often prevent immediate global collapse. Pressure signals, aided by turbulence, can still propagate across these scales. Gravity is strong, but not yet decisive. Within the same cloud, however, there are denser, colder regions. Filaments accumulate material. Shocks and turbulent compressions raise density in localized pockets. Cooling reduces temperature further. In these regions, the critical length becomes small enough that gravity can overcome pressure. Collapse begins there first, even while the surrounding cloud remains supported. This behavior produces a fragmentation cascade. The cloud does not collapse into one object. it breaks itself into smaller pieces, each governed by its own balance of forces. On the largest scale, the cloud fragments into clumps, regions tens of light years across with enhanced density. These clumps are still massive and still turbulent, but they are closer to instability than the cloud as a whole. Within clumps, the process repeats. Dense filaments and substructures emerge, shaped by turbulence and gravity working together. Some of these filaments exceed the local critical mass per unit length. Gravity begins to draw material inward along the filament's axis. The filament fragments further into cores, compact regions that are dense, cold, and gravitationally unstable. At each stage, the same principle applies. Gravity wins where pressure cannot respond fast enough. The scale shrinks, the density rises, and the temperature remains low thanks to efficient cooling. The critical thresholds move downward, allowing collapse to proceed step by step. There is no dramatic transition between stages, only a gradual handoff of dominance from pressure to gravity on progressively smaller scales. This cascade explains why star formation is inherently clustered. Stars rarely form in isolation because the collapse process itself creates groups. Cores form within clumps, clumps within clouds. The initial conditions of a star are shaped by the structure inherited from the cloud. The star's mass, environment, and companions are all influenced by how fragmentation unfolded long before the star existed. Despite its importance, the gene's instability operates slowly. The timescale for collapse is not instantaneous. Even once a region becomes unstable, gravity does not pull matter inward at arbitrary speed. The characteristic timescale is set by the freefall time, which depends on density. In dense cores, this can be hundreds of thousands of years. In larger clumps, it can be millions of years. Compared to human experience, this is unimaginably slow. Compared to galactic timescales, it is still measured and deliberate. The slowness of the process contributes to its invisibility. Early collapse does not produce bright radiation or violent motion. Infall speeds are often subsonic or only mildly supersonic. Gas continues to radiate energy away efficiently, preventing the buildup of heat or pressure that would announce dramatic change. Observationally, collapsing regions can look very similar to stable ones, especially when viewed from afar. Unevenness is another defining feature. Collapse does not proceed uniformly even within a single clump. Some regions cross the instability threshold earlier than others due to small differences in density, temperature, or turbulence. These differences can be seeded by turbulence itself. Random fluctuations become amplified by gravity. Once collapse begins in one region, it alters the surrounding environment, redistributing mass and energy in ways that influence neighbouring regions. This uneven progression ensures that molecular clouds are always in mixed states. Some parts are collapsing, others are stable, others may even be expanding or dispersing. The cloud as a whole never occupies a single, well-defined phase. This complexity makes it difficult to assign a simple evolutionary stage to a cloud. What matters is not the average condition, but the local conditions where gravity has gained an advantage. The invisibility of the gene's instability is also tied to observational limitations. The earliest stages of collapse involve changes in density and velocity that are subtle and distributed. They do not produce strong emission lines or sharp boundaries. Projection effects smear out signatures of infall. Turbulent motions mask coherent inward flow. Even when collapse is underway, it can be hard to prove observationally without detailed, high-resolution data. This has historically led to underestimation of how widespread collapse is within molecular clouds. Regions once thought to be static are now understood to host slow, systematic inflows. Filaments accrete material from their surroundings. Cores grow in mass over time. These processes were invisible until instrumentation and analysis techniques improved. The gene's instability also explains why star formation efficiency is low. Just because a cloud is massive does not mean most of its mass will collapse. Only regions that exceed the local thresholds participate. Much of the cloud remains below critical conditions and is eventually dispersed by feedback from newly formed stars or by galactic processes. Gravity wins often enough to form stars, but not so often that clouds are rapidly consumed. This balance is not accidental. It emerges naturally from the scale-dependent nature of the instability. If gravity dominated everywhere at once, galaxies would convert their gas into stars rapidly and exhaust themselves. If pressure always dominated, star formation would be rare or non-existent. The gene's instability provides a self-regulating pathway between these extremes. Another important aspect of the instability is that it does not require an external trigger. Collapse does not need a shock, a collision, or an explosion to begin. It can arise from internal evolution alone. Cooling lowers temperature, turbulence decays, density fluctuations persist. Eventually, a region crosses the threshold. From the outside, nothing appears to have happened. From the inside, gravity has quietly taken control. This internal origin is why collapse often appears uncorrelated with obvious external events. While shocks and feedback can influence where and when collapse occurs, they are not prerequisites. The fundamental driver is the gradual erosion of pressure support relative to gravity. This erosion is slow, uneven, and largely invisible. The gene's instability therefore represents a kind of inevitability rather than a trigger. Given enough time, cold, dense gas will fragment and collapse somewhere. The exact locations and outcomes depend on initial conditions and subsequent evolution, but the underlying logic is robust. Gravity does not need drama, it only needs patience. Over hundreds of thousands to millions of years, this patient process reshapes molecular clouds from within. Filaments grow denser, cores emerge. Mass redistributes itself along paths defined by gravity and limited by pressure. By the time a protostar forms and announces its presence through radiation and outflows, the decisive phase is already over. The outcome was determined earlier by thresholds crossed quietly in the dark. Seen in this light, the gene's instability is not just a criterion. It is a description of how structure emerges naturally in a cold, dissipative medium. It explains why collapse is fragmented rather than global, why it is slow rather than violent, and why it is so difficult to observe directly. Gravity wins not by force, but by waiting until nothing is left to stop it. Turbulence is one of the most counterintuitive ingredients in the life of a molecular cloud. In almost every other context, turbulence is associated with disorder, mixing, and destruction of structure. In molecular clouds, it does the opposite. It both delays gravitational collapse and creates the very conditions that allow collapse to begin. This dual role is not a contradiction. It is a consequence of how turbulence behaves in cold, compressible gas under the influence of gravity. The gas inside molecular clouds is not gently drifting. It moves violently by microscopic standards. Velocities of a few kilometers per second are common, even though the sound speed in gas at 10 Kelvin is only a few tenths of a kilometer per second. This means that turbulence in molecular clouds is typically supersonic. Shocks form naturally as faster-moving gas collides with slower material. These shocks compress gas abruptly, raising density without significantly raising temperature because the energy is radiated away efficiently. Supersonic turbulence is fundamentally different from the turbulence familiar in terrestrial fluids. In warm, incompressible fluids, turbulence tends to mix material and erase density contrasts. In cold, compressible gas, turbulence creates density contrasts. Shocks do not smooth out irregularities, they amplify them. Regions of gas become alternately rarefied and compressed, producing a complex filamentary density field. This is one of the primary reasons molecular clouds are structured rather than homogeneous. On the largest scales, turbulence acts as a source of support against gravity. The chaotic motion of gas contributes kinetic energy that counteracts gravitational potential energy. In this sense, turbulence plays a role analogous to pressure, even though it arises from bulk motion rather than thermal agitation. If turbulent velocities are high enough across a cloud, they can prevent global collapse, even if the cloud is massive and cold. This global support is statistical rather than uniform. Turbulence does not apply the same force everywhere at the same time. Instead, it maintains an average level of kinetic energy across large volumes. As long as that energy is present, gravity cannot easily draw the entire cloud inward. The cloud may oscillate, shear, and distort, but it does not collapse as a whole. This is why many molecular clouds persist for millions of years without undergoing rapid global contraction. Turbulence buys time. It slows down gravity by continually redistributing momentum. In this sense, turbulence is a stabilizing influence, and without it, molecular clouds would collapse much more quickly than observed. At the same time, turbulence is inherently local and intermittent. The same motions that support the cloud globally also generate localized compressions. When supersonic flows collide, shock fronts form. Across these fronts, gas density can increase by orders of magnitude. These compressed regions are colder, denser, and closer to gravitational instability than their surroundings. In these pockets, turbulence switches roles. Instead of opposing gravity, it helps gravity by concentrating mass. The increase in density shortens the local freefall time and lowers the threshold for collapse. Cooling remains efficient, so pressure does not rise enough to counteract the added gravity. What began as a random turbulent fluctuation becomes a seed for collapse. This is the heart of the paradox. Turbulence prevents collapse on large scales while triggering it on small scales. The same physical process both delays and enables star formation. There is no contradiction because the effect depends on scale. Turbulence injects energy at large scales and dissipates it at small scales. Gravity exploits the small-scale dissipation. The compressive nature of supersonic turbulence also explains the origin of filaments. When shocks intersect or propagate through inhomogeneous gas, they naturally produce elongated structures. Gas is swept into sheets and filaments where flows converge. These filaments are not static features. They accrete material from their surroundings, fed by the very turbulent motions that created them. Once a filament forms, gravity begins to matter more strongly along its length. Filaments can exceed critical mass thresholds, becoming unstable to fragmentation. Turbulence helped build the filament, but gravity takes over its evolution. The filament fragments into cores, and turbulence recedes to the background. Another crucial aspect of turbulence is that it decays. Turbulent motion is not self-sustaining. Energy cascades from large scales to smaller scales, where it is dissipated as heat through shocks and viscosity. In molecular clouds, this dissipation happens efficiently because cooling removes the generated heat almost immediately. As a result, turbulence loses energy rapidly, typically on timescales comparable to the cloud's crossing time. This decay has profound consequences. Unless turbulence is continuously driven, it cannot support the cloud indefinitely. Sources of turbulent driving include galactic shear, spiral arm passage, large-scale gas flows, and feedback from stars. Early in a cloud's life, these drivers may be strong enough to maintain high levels of turbulence. As time passes, driving weakens or becomes uneven, and turbulence begins to fade. When turbulence decays, its global support diminishes. Gravity does not weaken in response. The balance shifts. Regions that were marginally supported become unstable. Collapse accelerates, not because gravity suddenly changed, but because turbulence stopped doing its job. This transition is subtle and gradual, but it marks a turning point in the cloud's evolution. Importantly, turbulence does not decay uniformly. Some regions lose turbulent support faster than others. Dense regions dissipate turbulent energy more quickly because shocks are stronger and cooling is more effective. This selective decay further promotes local collapse. Turbulence essentially abandons the densest regions first, leaving gravity unopposed where it matters most. This behavior explains why turbulence creates structure instead of smoothing it out. In a warm, slowly cooling medium, turbulent energy would redistribute heat and homogenize density. In a cold, rapidly cooling medium, turbulent energy is lost before it can equilibrate the gas. Density contrasts persist and grow. Each shock leaves behind compressed regions that do not rebound fully because the excess energy is radiated away. The result is a highly intermittent medium, with dense filaments and cores embedded in more diffuse gas. Turbulence continuously sculpts this landscape, but it never erases it. Instead, it seeds gravitational instability by producing fluctuations that gravity can amplify. Another reason turbulence fails to smooth molecular clouds is that it is anisotropic. Magnetic fields guide motions along preferred directions, altering how shocks propagate and how structures form. Gas flows more easily along field lines than across them, reinforcing filamentary geometry. Turbulence and magnetic fields together impose order on chaos, channeling motion rather than randomizing it. The moment turbulence stops saving the cloud is not marked by any obvious event. There is no sudden stillness. Motions continue, but their character changes. Velocity dispersions decrease. Large-scale flows lose coherence. Energy injection no longer keeps pace with dissipation. Gravity, which has been present all along, begins to dominate more regions. At this stage, collapse becomes widespread, though still uneven. Filaments accrete faster. Cores grow more massive. Infall motions become more systematic. The cloud transitions from being turbulence-supported to gravity-dominated, not abruptly, but through a gradual reweighting of forces. From an observational standpoint, this transition is difficult to detect. Turbulence does not vanish. It weakens. Spectral lines narrow slightly. Infall signatures become more common but remain subtle. The cloud still looks chaotic, but the chaos now favors collapse rather than delay. This is why turbulence is often blamed or credited incorrectly for star formation. It is tempting to label turbulence as either a supporting mechanism or a triggering mechanism. In reality, it is both, at different times and scales. Turbulence sets the initial conditions for collapse and regulates its timing, but it does not determine the outcome alone. Gravity ultimately decides once turbulence no longer has the energy to interfere. The paradox of turbulence is therefore not a flaw in our understanding, but a feature of cold, dissipative systems. In molecular clouds, turbulence is a temporary ally of stability and a long-term accomplice of collapse. It builds structure while pretending to resist it. It delays gravity just long enough for gravity to organize its victory. Seen this way, turbulence is not noise in the star formation process. It is the mechanism that allows star formation to proceed slowly and selectively rather than catastrophically. Without turbulence, clouds would collapse too quickly. With too much turbulence, collapse would be suppressed entirely. The observed state of molecular clouds reflects a delicate balance, one that inevitably tips as turbulence decays. By the time stars begin to form in earnest, turbulence has already played its part. It assembled the filaments, seeded the cores, and then quietly stepped aside. What remains is gravity acting on a landscape that turbulence created but could not hold together. Magnetic fields are among the least intuitive forces shaping molecular clouds, largely because they are invisible and difficult to measure directly. Yet they permeate the interstellar medium and exert a subtle but persistent influence on how gas moves, fragments, and collapses. In molecular clouds, magnetic fields do not dominate dynamics in the way gravity does, nor do they inject energy like turbulence. Instead, they act as scaffolding, guiding motion, redistributing forces, and slowing down processes that would otherwise proceed too quickly. At first glance, it seems implausible that magnetic fields could matter in environments as massive as molecular clouds. The fields measured in these regions are weak by everyday standards, typically only a few microgauss to tens of microgauss. Such fields would have no noticeable effect on laboratory-scale systems or even on stellar interiors. The key difference lies in scale and coupling. Molecular clouds span tens to hundreds of light years and contain ionized particles mixed with neutral gas. Over these vast distances, even weak magnetic forces accumulate significant influence. The gas in molecular clouds is mostly neutral, but it is never perfectly so. A small fraction of particles are ionized by cosmic rays and background radiation. These charged particles are tied to magnetic field lines, moving along them rather than across them. Through collisions, they drag neutral particles with them. This coupling allows magnetic fields to influence the bulk motion of gas, even though most of the mass is neutral. The result is a medium that responds neither like a pure plasma nor like a purely neutral gas, but something in between. One of the most important consequences of this coupling is that magnetic fields resist compression perpendicular to their direction. Gas can flow relatively easily along field lines, but motion across them is impeded. This anisotropy shapes the structure of molecular clouds from the outset. Filaments tend to align with magnetic fields, or to form in ways that reflect the local field geometry. Collapse, when it begins, often proceeds preferentially along these directions of least resistance. The concept of flux freezing helps explain why magnetic fields remain important even as clouds evolve. In ideal magnetized fluids, magnetic field lines are said to be frozen into the gas. As gas moves and contracts, it drags field lines with it. The field strength increases as the gas density increases, amplifying magnetic effects in denser regions. In reality, molecular clouds are not perfectly ideal fluids, but flux freezing remains a useful approximation over large scales. Flux freezing implies that as a cloud contracts, magnetic pressure and tension grow. This provides increasing resistance to further contraction, particularly across field lines. In the early stages of cloud evolution, this effect can be significant. Regions that might otherwise collapse under gravity find themselves partially supported by the growing magnetic field. Collapse slows, and in some directions it is temporarily halted. However, flux freezing is not absolute. Molecular clouds are weakly ionized, and neutral particles can slowly drift relative to the magnetic field. This process is known as ambipolar diffusion. Over time, neutrals slip past ions and field lines, allowing mass to concentrate without dragging all the magnetic flux with it. Ambipolar diffusion is slow, operating over timescales comparable to or longer than the lifetime of a cloud, but its cumulative effect is crucial. Through ambipolar diffusion, dense regions gradually decouple from magnetic support. Gravity pulls neutral gas inward, while magnetic fields lag behind, anchored by the ionized component. As mass accumulates in a region without a proportional increase in magnetic flux, the local mass-to-flux ratio increases. Once this ratio exceeds a critical value, magnetic support can no longer prevent collapse. This is why magnetic fields delay collapse rather than prevent it. They impose a timescale. They regulate how quickly gas can reorganize itself under gravity. In magnetically supported regions, collapse is not forbidden. It is slowed. The cloud enters a prolonged metastable phase, during which gravity and magnetic forces remain in tension. Eventually, diffusion and accumulation tip the balance. This delayed collapse has important consequences for star formation. It stretches the timeline, allowing turbulence to decay, cooling to proceed, and structure to develop hierarchically. It also introduces selectivity. Not all regions decouple at the same rate. Dense pockets with favourable conditions overcome magnetic support earlier than others. As a result, star formation occurs in discrete locations rather than uniformly across the cloud. Observational evidence for magnetic fields in molecular clouds comes primarily from polarization measurements. Dust grains within clouds are not spherical. They tend to align their long axes perpendicular to the local magnetic field due to interactions between rotation, radiation, and magnetic torques. As a result, light passing through or emitted by these grains becomes polarized in a way that reflects the field orientation. By mapping polarized emission in the infrared and submillimeter, astronomers can infer the geometry of magnetic fields across clouds. These maps reveal coherent field structures extending over large distances, often aligned with filaments or wrapping around dense regions. The fields are not random or tangled beyond recognition. They exhibit ordered patterns that suggest a dynamic role in shaping cloud structure. Polarization observations also show that magnetic fields become more ordered in denser regions. This is consistent with flux, freezing, and compression. As gas accumulates, field lines are drawn closer together, enhancing both field strength and coherence. In some cases, the field geometry appears to channel material into filaments, guiding accretion flows toward dense cores. These observations reinforce the idea that collapse happens along field lines. Gas flows more easily in directions parallel to the magnetic field, where there is little magnetic resistance. Perpendicular motion requires bending or compressing field lines, which costs energy. As a result, early collapse often takes the form of elongated structures rather than spherical contraction. Filaments form first, then fragment into cores. This anisotropic collapse affects the angular momentum of forming stars. As gas flows along field lines into a collapsing core, magnetic forces can transfer angular momentum outward. This process, known as magnetic braking, plays a crucial role in regulating rotation. Without it, collapsing cores would spin up rapidly as they contract, potentially preventing further collapse or producing excessively large disks. Magnetic braking works by coupling rotating gas to the surrounding medium through magnetic field lines. As the inner region spins, it twists the field lines, generating magnetic torques that transport angular momentum away. This allows material to continue falling inward rather than piling up in a rapidly rotating configuration. The efficiency of this process depends on field strength, geometry, and ionization, but its impact is profound. Angular momentum loss is essential for star formation. The angular momentum of a typical molecular cloud core is orders of magnitude larger than what a star can retain. Most of it must be removed or redistributed. Magnetic braking provides a natural mechanism for this removal, operating early in the collapse process before disks and stars fully form. At the same time, magnetic braking is not infinitely efficient. In very dense regions where ionization drops and ambipolar diffusion becomes more effective, coupling weakens. Angular momentum transport slows, allowing disks to form around protostars. The balance between magnetic braking and diffusion helps set the size and structure of these disks, influencing later stages of planet formation. Magnetic fields therefore act across multiple stages of collapse. They shape large-scale cloud structure, regulate the onset of instability, guide flows into filaments, delay collapse through support, and redistribute angular momentum during core formation. At no point do they completely dominate, but at every stage they leave an imprint. The subtlety of magnetic influence contributes to its historical underestimation. Unlike gravity, which produces obvious motion or turbulence, which produces broad velocity signatures, magnetic fields work quietly. Their effects are geometric and temporal rather than explosive. They alter pathways rather than outcomes. This makes them harder to isolate and easier to overlook. Yet without magnetic fields, molecular clouds would behave very differently. Collapse would proceed more rapidly and more isotropically. Angular momentum problems would be more severe. Structure would be less filamentary and more chaotic. The observed properties of star-forming regions would be difficult to reproduce. The invisible scaffolding provided by magnetic fields is therefore not optional. It is an integral part of how molecular clouds evolve. It ensures that collapse is delayed, structured, and regulated rather than immediate and catastrophic. It gives gravity time to work selectively rather than indiscriminately. In the end, magnetic fields do not decide where stars form, but they influence how and when. They shape the environment in which gravity operates, guiding collapse along certain paths while resisting it along others. Their role is not to stop star formation, but to choreograph it. This choreography unfolds slowly over millions of years, in regions that appear dark and quiet. Magnetic field lines thread through the gas, unseen but active, bending and twisting as mass accumulates and moves. By the time a star ignites and begins to dominate its surroundings, the magnetic field has already done much of its work, quietly scaffolding the collapse that made the star possible. When people imagine gravitational collapse, they often picture something violent, an implosion, a flash of light, a sudden release of energy. This intuition is shaped by familiar astrophysical events such as supernova, stellar collisions, or black hole mergers, where gravity is associated with catastrophe and brilliance. The collapse of a molecular cloud is the opposite of this picture. It is one of the quietest, large-scale transformations in the universe. There is no explosion, no shockwave racing outward, no sudden brightening. The most important phase of collapse happens almost without a trace. The absence of drama is not an accident. It is a direct consequence of the physical conditions inside molecular clouds. These environments are cold, dissipative, and efficient at losing energy. Gravity does not accelerate matter into violent motion because any energy gained through contraction is quickly removed. Collapse proceeds not as a fall, but as a slow settling. In the earliest stages, infall velocities are typically subsonic. Gas moves inward at speeds lower than the speed of sound in the medium. This immediately rules out strong shocks. Shocks require supersonic motion, where information cannot propagate ahead of the flow. In molecular clouds, pressure waves can still travel faster than the infalling gas, smoothing out abrupt changes. The gas adjusts continuously as it moves inward rather than piling up violently. This subsonic character is crucial. It means that collapse does not announce itself through sudden compression fronts or abrupt heating. Instead, density increases gradually. Temperature remains nearly constant due to efficient cooling. From the outside, the cloud looks almost unchanged, even as its internal state evolves steadily toward instability. The reason energy does not accumulate lies in radiative cooling. As gas contracts under gravity, gravitational potential energy is converted into kinetic energy and then into thermal energy. In many astrophysical environments, this thermal energy builds up, increasing pressure and producing radiation only after temperatures rise dramatically. In molecular clouds, this energy is radiated away almost immediately, primarily in infrared and millimeter wavelengths. Molecular line emission and dust emission act as continuous exhaust channels. Each small increase in temperature caused by compression is countered by radiation escaping the cloud. The energy does not remain stored, it leaves. As a result, pressure does not rise significantly. Gravity never encounters a strong rebound force. Collapse continues quietly, step by step. This behavior stands in stark contrast to a supernova. In a supernova, energy is trapped. Nuclear reactions or core collapse release enormous amounts of energy faster than it can be radiated away. Pressure builds catastrophically. Shock waves form. Matter is expelled at thousands of kilometers per second. The event is bright because energy is concentrated and released violently. Molecular cloud collapse works in reverse. Energy is not injected, it is removed. There is no sudden release because there is no accumulation. Gravity converts potential energy into heat, and the cloud immediately disposes of that heat. Instead of exploding outward, the system sinks inward, quietly lowering its total energy state. This is why collapse produces no flash. Light is emitted continuously but faintly, spread across large volumes and long timescales. There is no moment when energy output spikes dramatically. The cloud simply glows weakly in the infrared, if at all. Even this glow is difficult to detect, often lost against the background emission of the galaxy. Sound is also absent in any meaningful sense. Sound requires pressure waves propagating through a medium. While such waves exist locally, there is no coherent acoustic event associated with collapse. Subsonic motion does not generate strong compressive waves. Any disturbances are damped by cooling and dispersion. The collapse is not accompanied by a bang or a rumble. It is closer to a whisper spread over millions of years. The silence is both literal and physical. There is no mechanism to produce rapid, large-scale oscillations. The cloud adjusts smoothly to changing conditions. Each region responds to gravity in near equilibrium with its surroundings. Even when infall accelerates later in the collapse, the process remains controlled until very late stages, when protostellar objects finally form and introduce new energy sources. Another reason collapse lacks spectacle is that it is highly fragmented. There is no single collapsing front. Different regions evolve at different rates. Energy release is distributed among countless small-scale processes rather than concentrated in one event. This fragmentation further suppresses dramatic signatures. Nothing happens everywhere at once. The notion that collapse should be explosive often stems from misunderstanding gravitational energy. Gravity itself does not create explosions. Explosions occur when energy is suddenly released into a confined region. In molecular clouds, gravity releases energy gradually, and the cloud is anything but confined. Radiation escapes easily. There is no build-up, no pressure cooker waiting to burst. In fact, collapse can be thought of as the universe doing bookkeeping. The system is shedding energy to move toward a lower energy configuration. Every photon emitted during cooling represents a small reduction in the cloud's total energy. Over millions of years, these tiny losses add up. The cloud slowly transitions from a diffuse, supported structure to a denser, gravitationally bound one. This process reflects a deeper principle. Most structure in the universe forms through dissipation, not violence. Galaxies form as gas radiates energy and settles into disks. Stars form as clouds cool and contract. Planets form as disks lose energy and angular momentum. Explosive events are the exception, not the rule. They are memorable because they are rare and bright, not because they are the dominant mode of cosmic evolution. The quietness of collapse also explains why it was so difficult to recognize observationally. For decades, molecular clouds were seen as static objects. The lack of obvious motion or emission was interpreted as inactivity. Only with improved sensitivity and resolution did astronomers begin to detect subtle infall signatures, velocity gradients, and cold dust emission indicating ongoing collapse. Even now, much of the energy loss associated with collapse remains hidden. Infrared photons from cold dust blend into the galactic background. Molecular line emission spreads across wide velocity ranges. The signal of collapse is not a spike, but a bias, a slight asymmetry, a systematic drift buried in noise. Detecting it requires patience and careful analysis. The idea that the universe loses energy quietly is not poetic exaggeration. It is a literal description of how gravity operates in dissipative systems. The second law of thermodynamics favors states of lower free energy. Molecular cloud collapse is one pathway by which the universe follows that law. Energy is radiated away, entropy increases, and structure emerges. From this perspective, the silence of collapse is not surprising, it is expected. Loud events require special conditions, rapid energy injection, confinement, or explosive feedback. The formation of stars begins under the opposite conditions: slow energy loss, open systems, and efficient cooling. The spectacular phases come later, when newly formed stars inject energy back into their surroundings. Until then, collapse remains a background process. It does not interrupt the galaxy. It does not announce itself across space. It simply proceeds, guided by gravity and enabled by cooling, lowering the energy of the system one photon at a time. In the end, the absence of an explosion is the defining feature of molecular cloud collapse. It tells us that star formation is not triggered by violence, but by patience. The universe does not shout when it builds stars. It whispers steadily over millions of years, losing energy quietly until something new can finally ignite. Prestellar cores represent the most decisive threshold crossed during the collapse of a molecular cloud. They are the first structures that can truly be called bound, self-gravitating objects rather than transient fluctuations. Yet even at this stage, nothing dramatic announces their birth. There is no ignition, no sudden brightening, no violent restructuring of the cloud. A prestellar core forms when a region becomes dense and cold enough that gravity dominates all remaining forms of support, but the transition is gradual and easy to miss. A defining characteristic of prestellar cores is density. While the average density of a molecular cloud may be only a few hundred particles per cubic centimetre, prestellar cores reach densities many orders of magnitude higher. Typical values rise to hundreds of thousands or even millions of particles per cubic centimetre. This increase is not uniform across the cloud. It occurs in localized pockets where turbulence has compressed gas, cooling has removed pressure, and magnetic support has weakened sufficiently. These density thresholds are not arbitrary. They reflect the point at which the local gravitational potential overwhelms thermal pressure, turbulent motions, and magnetic resistance on the scale of the core. Below this threshold, a dense region may still be transient, dispersing as turbulence shifts or as external pressure changes. Above it, the region becomes bound. Even if external forces act upon it, the core tends to persist and evolve inward rather than dissolve. Temperature plays an equally crucial role. As density increases, prestellar cores cool efficiently through dust emission and molecular line radiation. Temperatures typically drop to around 10 Kelvin, roughly minus 263 degrees Celsius, or minus 441 degrees Fahrenheit. In some cases, temperatures can fall even lower in the densest interiors. At these temperatures, thermal pressure is minimal, the sound speed is low, and pressure gradients are weak. This combination of high density and low temperature is what defines a prestellar core physically. Gravity has a clear advantage, and the characteristic timescale for further collapse shortens dramatically. Yet despite this, prestellar cores are still starless. There is no central object, no nuclear fusion, and no strong internal energy source. All energy continues to be lost through radiation. Observationally, prestellar cores are most clearly identified in the far infrared and submillimeter. At optical wavelengths, they are completely opaque, appearing as dark silhouettes against background starlight. At infrared wavelengths, they do not shine brightly like protostars. Instead, they emit faint thermal radiation from cold dust. This emission peaks in the far infrared, making it accessible only to sensitive instruments designed to observe cold environments. Far infrared maps reveal prestellar cores as compact, cold regions embedded within larger molecular clouds. They often sit along filaments, marking the densest points where material has accumulated. Temperature maps derived from multi-wavelength observations show clear minima at core locations, confirming that these regions are colder than their surroundings. Velocity measurements indicate reduced turbulence compared to the surrounding gas, consistent with energy dissipation and gravitational dominance. Despite the importance of prestellar cores as precursors to stars, most of them never form stars. This is one of the central puzzles of star formation. Molecular clouds contain many dense cores, but only a fraction proceed to collapse into protostars. The rest stall, disperse, or are disrupted before reaching the next stage. Several factors contribute to this high failure rate. Some cores are only marginally bound. Small changes in external pressure, turbulence, or radiation can push them back below the instability threshold. Others may be stripped of mass by nearby activity or disrupted by feedback from star formation elsewhere in the cloud. In crowded environments, competition for material can starve some cores while others grow. Timescale is another limiting factor. Even a bound core must continue to lose energy and angular momentum to collapse fully. If this process is interrupted, collapse can halt. Turbulence may re-enter the region. Magnetic fields may temporarily regain influence. External radiation may heat the core slightly, increasing pressure just enough to slow or stop infall. This leads directly to the efficiency problem of star formation. On galactic scales, only a small fraction of molecular gas ends up in stars. Even within molecular clouds, only a small fraction of dense gas produces stars. And even within prestellar cores, the conversion from gas to stars is far from guaranteed. Each stage filters material further, reducing efficiency. This inefficiency is not a flaw in the process, it is a regulatory mechanism. If every dense core formed a star, galaxies would convert their gas into stars far too quickly. The observed low efficiency ensures that star formation is spread out over billions of years, allowing galaxies to persist and evolve. The existence of many failed cores implies that molecular clouds contain a kind of graveyard. These are regions where collapse began but did not complete. The gas became dense and cold. Gravity gained influence, but the process stalled. Over time, such cores may re-expand, fragment further, or merge with surrounding material. Their histories are written into the density structure of the cloud, but they leave no stars behind. Observationally, these failed cores are difficult to distinguish from successful ones until late stages. Both appear cold, dense, and starless. Only detailed measurements of mass, temperature, velocity structure, and environment can hint at their fate. Some may hover near the threshold for millions of years before dispersing quietly. The presence of this graveyard highlights an important truth. Prestellar cores are not destiny. They represent potential, not outcome. Crossing the density and temperature thresholds necessary for core formation is a necessary step toward star formation, but it is not sufficient. The environment continues to matter. The balance of forces remains delicate. From a physical standpoint, prestellar cores mark the point where gravity becomes locally dominant, but not yet unstoppable. They are the last stage where collapse can still fail without leaving a permanent mark. Once a protostar forms, feedback mechanisms change the environment irreversibly. Before that point, the system remains flexible. The study of prestellar cores therefore offers insight not only into how stars form, but into how often they do not. It reveals that the universe is conservative with its raw material, allowing gravity many opportunities to fail before it succeeds. The silence of these failures is as important as the brilliance of successful star formation. In this sense, prestellar cores are a quiet census of unrealized possibilities. Each cold, dense knot in a molecular cloud represents a path that might have led to a star but did not. The cloud remembers these attempts through its structure, but the galaxy moves on, slowly recycling the material. Understanding prestellar cores requires accepting that star formation is not a simple pipeline. It is a probabilistic process shaped by thresholds, delays, and interruptions. The birth of a core is a critical step, but it is not a guarantee. Gravity may have gained ground, but it has not yet won. Only when a core crosses the next boundary, forming a protostar and trapping energy rather than losing it, does collapse become irreversible. Until then, prestellar cores remain suspended between possibility and dissolution, quietly marking the line between what could be and what will never be. Feedback is often described as the mechanism that regulates star formation. the process by which newly formed stars inject energy back into their environment and prevent molecular clouds from collapsing completely. In a broad galactic sense, this description is correct. Over long timescales, feedback disperses clouds, heats, gas, and limits how much material ends up locked into stars. But when examined at the scale of individual molecular clouds and prestellar structures, feedback arrives late. By the time it becomes dynamically important, gravity has already done most of its work. Collapse has begun, structure has formed, and the outcome is largely decided. This timing mismatch is critical. Feedback does not prevent collapse from starting. It reacts to collapse after it is already underway. In that sense, feedback shapes the aftermath of star formation more than its initiation. It sculpts what remains, not what has already fallen inward. The first form of feedback to appear comes from protostars themselves, long before nuclear fusion ignites in their cores. As gas accretes onto a forming protostar, it does not fall straight in. Conservation of angular momentum forces the material into a rotating disk. From this disk, powerful collimated jets and broader outflows are launched along the rotation axis. These protostellar jets are among the earliest energetic phenomena associated with star formation. Despite their dramatic appearance in images, protostellar jets are not particularly efficient at halting collapse. They are highly directional. Most of their energy and momentum are channeled into narrow beams that punch through the surrounding cloud rather than coupling strongly to it. The jet clears polar cavities, carving channels through which material is expelled, but the bulk of the cloud, especially in the equatorial plane, remains largely unaffected. Outflows do remove mass from the immediate vicinity of the protostar. They can limit the final mass of the star by ejecting a fraction of the accreting material. They also stir the surrounding gas, injecting turbulence locally. But this influence is confined to relatively small regions. The dense filaments feeding the core often continue to deliver material even as outflows operate, flowing in from directions the jet does not reach. Crucially, protostellar outflows turn on only after a prestellar core has already collapsed into a protostar. By that point, the local gravitational potential well is deep, and infall has become concentrated. The jet cannot reverse this process. It can reduce efficiency, redistribute material, and shape the immediate environment, but it cannot erase the fact that collapse succeeded. As stars grow more massive and luminous, radiative feedback becomes important. Radiation pressure, heating, and ionization begin to alter the surrounding gas. Ultraviolet photons from young stars ionize hydrogen, creating expanding regions of hot, ionized gas. These ionization fronts can drive shocks into the surrounding molecular material, compressing some regions while dispersing others. Again, timing matters. Ionization fronts develop only once stars are already shining strongly. By then, the cloud has fragmented, cores have formed, and some stars are already in place. Ionizing radiation tends to affect the lower density gas first, flowing preferentially into cavities and along paths of least resistance. Dense filaments and cores are more resistant, shielded by dust and geometry. Radiation pressure itself is often invoked as a way to halt accretion, especially in the context of massive star formation. Photons carry momentum, and when absorbed or scattered by dust, they can exert an outward force. In practice, this force competes with gravity, but rarely overwhelms it entirely at early stages. Gas finds ways around radiation barriers, flowing through dense channels and along disk planes where shielding is strongest. Ionization fronts also do not propagate instantaneously. Their expansion is governed by recombination, density structure, and geometry. In a clumpy, filamentary cloud, ionized regions expand unevenly, wrapping around dense structures rather than destroying them outright. Some regions are compressed by the advancing front, potentially triggering additional collapse nearby. Others are eroded and dispersed. This leads to a counterintuitive result. Feedback can both suppress and promote star formation locally. It removes gas from some regions while compressing it in others. However, even when it triggers new collapse, it does so using material that is already marginally unstable. Feedback reshuffles where stars form more than whether they form at all. The key limitation of feedback as a preventive mechanism is that it operates on timescales comparable to or longer than collapse itself. Once a region exceeds critical thresholds and begins collapsing, the free fall time shortens dramatically. Gravity accelerates the process. Feedback, by contrast, must first be generated by newly formed stars and then propagate through a complex medium. It is always responding to events that have already happened. This is why feedback shapes but does not stop collapse. It regulates efficiency rather than initiation. It determines how much mass ends up in stars, how clustered those stars are, and how long star formation persists in a given cloud. It does not rewind the process. Star formation is therefore self-terminating, but not self-preventing. Once stars begin to form, they sow the seeds of the cloud's destruction. Jets, winds, radiation, and eventually supernova inject energy and momentum into the surrounding gas, increasing turbulence, heating material, and dispersing dense structures. Over time, this feedback unbinds the cloud, returning much of its mass to the diffuse interstellar medium. This termination is not immediate. Clouds often continue forming stars for several million years after the first stars appear. Feedback gradually erodes the cloud, carving cavities, dispersing envelopes, and breaking filaments. Star formation slows as dense gas is consumed or expelled. Eventually, the cloud can no longer sustain collapse anywhere, and star formation ceases. Importantly, this destruction occurs after collapse has already begun in many regions. The stars that form early are not undone. The cloud is sacrificed to limit further star formation, not to prevent the initial generation. In this sense, molecular clouds are disposable structures. They exist to create stars and are destroyed in the process. The most dramatic feedback arrives last, in the form of supernovae from massive stars. These explosions inject enormous energy into the surrounding medium, driving strong shocks and heating gas to extreme temperatures. By the time supernovae occur, the original molecular cloud is often already fragmented or partially dispersed. The explosion finishes the job, sweeping up remaining material and mixing it back into the galaxy. From the perspective of the cloud's evolution, supernovae are an epilogue, not a cause. They do not regulate the earliest stages of collapse. They reset the environment for the next generation of clouds. This sequence reveals an important asymmetry. Gravity acts continuously from the beginning, shaping structure quietly and persistently. Feedback acts episodically and reactively, responding to the consequences of gravity rather than anticipating them. The outcome is a universe where star formation is inevitable wherever conditions allow collapse to begin, but limited in scope and duration by the aftermath. The phrase, "too late to save the cloud," captures this asymmetry precisely. By the time feedback is strong enough to matter globally, the cloud's fate is sealed. Its internal structure has crossed critical thresholds. Its densest regions are bound. Its collapse has become irreversible in those zones. Feedback cannot rewind time. It can only clear the stage. This delayed intervention is essential for galactic evolution. If feedback acted earlier or more efficiently, star formation might be suppressed entirely. If it acted later or less effectively, clouds might convert too much mass into stars. The observed balance suggests that the universe has found a regime where feedback intervenes just late enough to regulate, but not erase, gravitational collapse. From an energetic standpoint, this makes sense. Early in a cloud's life, there are no strong energy sources. Gravity is the only game in town, and it operates quietly. Feedback requires stars, and stars require collapse. Regulation cannot precede creation. The role of feedback is therefore not to prevent stars from forming, but to ensure that star formation remains localized, inefficient, and temporary. It is a cleanup process, not a gatekeeper. It ends episodes of star formation rather than deciding whether they begin. Seen this way, feedback is the universe's way of closing loops. Gas collapses, stars form, energy is injected, clouds disperse, and material returns to the diffuse medium, ready to begin the cycle again elsewhere. Each generation inherits the consequences of the last. The silence of early collapse and the violence of late feedback are two halves of the same story. The quiet phase assembles structure patiently. The loud phase dismantles it. One cannot occur without the other, but they do not overlap in time or function. By the time feedback roars to life, the most important work has already been done in silence. Gravity has already chosen its winners. Feedback merely ensures that the game does not go on forever in the same place. Real molecular clouds do not collapse in a single idealized way. Theoretical frameworks describe thresholds, instabilities, and balances of forces, but it is only by examining actual clouds that the full complexity becomes clear. Observations show that collapse depends strongly on environment, scale, and history. Clouds with similar masses can behave very differently. Clouds in the same galaxy can follow distinct evolutionary paths. There is no universal template for collapse, only a set of physical principles expressed in different ways. 3 nearby molecular cloud complexes illustrate this clearly: the Orion molecular cloud, the Taurus molecular cloud, and the Perseus molecular cloud. Each is actively forming stars. Each contains cold, dense gas undergoing collapse. Yet the structure, efficiency, and outcome of collapse in each case are strikingly different. The Orion molecular cloud is the most massive and energetic of the 3. It spans well over 100 light-years and contains hundreds of thousands of solar masses of molecular gas. It is associated with massive star formation, bright nebulae, and strong feedback. From an observational standpoint, Orion is loud. Ionized gas glows brightly. Jets, outflows, and radiation fields are intense. This makes it tempting to associate collapse here with violence and disruption. Yet, when examined carefully, Orion still follows the same quiet logic of collapse seen elsewhere. Dense filaments dominate its structure. Cold prestellar cores are embedded within these filaments, shielded from the intense radiation nearby. The earliest stages of collapse in Orion were not explosive. They occurred deep within cold, dusty regions long before massive stars ignited. Gravity acted locally, fragmenting the cloud into clumps and cores in much the same way as in quieter environments. What distinguishes Orion is what happens afterward. The presence of massive stars means feedback becomes strong quickly. Ionization fronts expand. Radiation pressure sculpts cavities. Stellar winds inject energy. As a result, collapse is truncated spatially and temporally. Star formation is efficient in localized regions but does not consume the entire cloud. The environment becomes hostile to further collapse relatively early, and the cloud is dispersed on shorter timescales than lower mass regions. In contrast, the Taurus molecular cloud represents a radically different regime. Taurus is lower in mass, lower in density, and largely devoid of massive stars. It forms predominantly low-mass stars in relative isolation. There are few bright nebulae, little ionized gas, and minimal large-scale feedback. Taurus is quiet not only in appearance, but in outcome. Collapse in Taurus proceeds slowly and gently. Filaments dominate the structure, but they are thinner and less crowded than in Orion. Prestellar cores are more widely spaced. Infall rates are low. Feedback from young stars is weak, consisting mainly of modest outflows that affect only their immediate surroundings. As a result, the cloud persists for a long time, continuing to form stars at a low rate without rapidly destroying itself. Taurus teaches an important lesson. Collapse does not require violence or extreme conditions. Gravity can operate efficiently even in relatively calm environments, provided the gas is cold and dense enough. The absence of massive stars means that feedback does not quickly shut down star formation. Instead, collapse and star formation proceed in a drawn-out, inefficient manner, producing a sparse population of low-mass stars over millions of years. The Perseus molecular cloud occupies an intermediate position between Orion and Taurus. It is more massive and active than Taurus, but far less extreme than Orion. Perseus forms stars in clusters rather than isolation, but these clusters are modest in size. Feedback is present, but not overwhelming. Collapse is neither explosive nor minimal. It is clustered and structured. In Perseus, observations reveal networks of filaments feeding material into dense hubs where multiple cores form in close proximity. These hubs are sites of clustered collapse, where gravity organizes material on relatively small scales. Turbulence and magnetic fields shape the inflow, while cooling keeps temperatures low. Prestellar cores form in groups, leading to the birth of stellar clusters rather than isolated stars. The clustered nature of collapse in Perseus highlights the role of environment in setting spatial outcomes. Where gas flows converge and density builds up, collapse becomes collective. Multiple cores influence one another gravitationally. Competition for material becomes important. Feedback from young stars begins to overlap, affecting neighbouring cores. The result is a more complex interplay between collapse and disruption than in Taurus, but without the overwhelming feedback seen in Orion. Comparing these three regions makes it clear that there is no single collapse pathway. All three clouds obey the same physical laws. Gravity, turbulence, cooling, magnetic fields, and feedback are present in all cases. What differs is their relative importance, timing, and geometry. In Orion, high mass and dense clustering mean that massive stars form early and feedback rapidly reshapes the cloud. Collapse is efficient locally but short-lived globally. In Taurus, low mass and sparse structure mean that collapse proceeds slowly, feedback is weak, and the cloud survives longer. In Perseus, intermediate conditions lead to clustered but regulated star formation. These differences are not superficial. They affect the masses of stars formed, the clustering properties of stellar populations, and the lifetime of the cloud itself. They also affect how much gas is returned to the interstellar medium and on what timescales. A galaxy populated only by Orion-like clouds would evolve very differently from one dominated by Taurus-like regions. Another key lesson from these case studies is that initial conditions matter, but history matters just as much. The way a cloud assembled, the flows that fed it, and the environment it inhabits all influence how collapse unfolds. A cloud formed primarily through spiral arm compression may behave differently from one assembled by converging flows or past feedback. These differences persist through the collapse process. Observations also show that clouds rarely evolve in isolation. They are embedded in larger galactic structures. External pressure, shear, and radiation fields all modulate collapse. Two clouds with similar internal properties can follow different paths simply because they reside in different parts of the galaxy. The absence of a single collapse pathway explains why star formation theories must be statistical rather than deterministic. It is not possible to predict the fate of a cloud based on one parameter alone. Mass, density, temperature, turbulence, magnetic field strength, and environment all interact. Small differences early on can lead to divergent outcomes later. Importantly, these case studies reinforce a central theme. Collapse begins quietly everywhere. Whether the end result is a blazing nebula or a handful of faint stars, the initial phase is always cold, slow, and hidden. The differences emerge later, when feedback and environment amplify small initial variations. In this sense, Orion, Taurus, and Perseus are not exceptions to a rule. They are expressions of it. They demonstrate how the same underlying physics produces diversity rather than uniformity. Gravity does not impose a single script. It works with what it is given. Understanding real molecular clouds therefore requires abandoning the idea of a standard model of collapse. There is no average cloud, no typical outcome. There are only ranges of behavior constrained by physics and shaped by circumstance. The universe does not repeat itself exactly when forming stars. it improvises within limits. These case studies show that collapse is robust but flexible. It happens under many conditions, but it does not look the same everywhere. The variety of star-forming regions we observe is not noise around a simple picture. It is the picture. By studying real clouds in detail, astronomers are not just testing theory. They are revealing the range of possibilities allowed by gravity acting in a cold, complex medium. That range is wide enough to encompass violent clusters and quiet isolation, rapid disruption and long-lived persistence, all arising from the same silent beginnings. The collapse of molecular clouds may seem like a small-scale local process confined to dark regions within galaxies, but its consequences extend far beyond the birth of individual stars. This quiet, inefficient and prolonged mechanism shapes how galaxies grow, how matter is recycled, how chemical complexity arises, and how the universe evolves over billions of years. In a very real sense, the large-scale behavior of the universe is regulated by the slowness and subtlety of molecular cloud collapse. At the most immediate level, molecular cloud collapse controls the star formation rate. Galaxies contain vast reservoirs of gas, often enough to form stars at rates far higher than what is observed. If gravity alone determined outcomes, galaxies would rapidly convert their gas into stars and exhaust themselves early in cosmic history. Instead, star formation proceeds slowly. Only a small fraction of molecular gas collapses at any given time, and only a fraction of that ends up in stars. The rest remains in clouds, disperses, or is recycled. This regulation arises directly from the physics of collapse. Cooling, turbulence, magnetic fields and feedback all conspire to delay and fragment gravitational contraction. Collapse occurs locally rather than globally, unevenly rather than uniformly. As a result, star formation is throttled. Galaxies form stars not as fast as they can, but as slowly as molecular clouds allow. This bottleneck is essential. Without it, the observable universe would look radically different, dominated by early bursts of star formation followed by long periods of inactivity. The regulated pace of star formation also governs chemical enrichment. Stars are the primary factories of heavy elements. Through nuclear fusion and stellar explosions, they produce carbon, oxygen, nitrogen, iron, and all the elements required for complex chemistry. These elements are returned to the interstellar medium through winds, outflows, and supernovae, enriching future generations of gas and stars. If molecular clouds collapsed rapidly and efficiently, chemical enrichment would be abrupt and uneven. Instead, the slow formation of stars spreads enrichment over long timescales. Each generation of stars slightly alters the chemical makeup of the galaxy, incrementally increasing metallicity. This gradual process allows galaxies to evolve chemically in a controlled way, avoiding extreme early enrichment and preserving diversity in stellar populations. Chemical enrichment feeds back directly into molecular cloud physics. Dust grains, which are essential for cooling and molecule formation, are made of heavy elements. As galaxies enrich, dust abundance increases, making it easier for molecular clouds to form and collapse. This creates a long-term feedback loop. Slow star formation produces gradual enrichment, which in turn subtly alters future star formation without ever triggering runaway behavior. Planet formation is another delayed consequence of this process. Planets form from the leftover material in disks around young stars, material that itself originated in molecular clouds. The availability of heavy elements determines whether rocky planets can form at all, and influences the composition of gas giants, atmospheres, and planetary systems. Because molecular cloud collapse regulates when and where stars form, it indirectly regulates when and where planets can form. The universe did not produce planets immediately. It required multiple generations of slow, inefficient star formation to enrich the interstellar medium sufficiently. Planet formation is therefore not a primary process, but a secondary one, contingent on the quiet accumulation of complexity over time. This delay has profound implications. It means that habitable environments could not arise until the universe had already aged significantly. The conditions necessary for planets, and ultimately for life, are inseparable from the slow collapse of molecular clouds. The silence of early star formation set the stage for complexity billions of years later. On galactic scales, the slow collapse of molecular clouds explains why galaxies evolve gradually rather than catastrophically. Galaxies are dynamic systems, constantly accreting gas, forming stars, and interacting with their environment, yet their overall appearance and structure change slowly. Spiral arms persist, disks remain thin. Star formation rates decline gently rather than abruptly. This stability is not imposed from above. It emerges from the inefficiency of molecular cloud collapse. Because gas is converted into stars slowly, galaxies retain large gas reservoirs for extended periods. This allows continued star formation, sustained spiral structure, and long-term dynamical equilibrium. The slow pace of collapse acts as a governor on galactic evolution. Even dramatic events such as galaxy mergers do not completely override this regulation. Mergers can compress gas and enhance star formation temporarily, but even then, starbursts are limited in duration and efficiency. Molecular cloud physics still applies. Collapse accelerates locally, but feedback and inefficiency prevent total gas consumption. The same quiet processes reassert control once the disturbance passes. On cosmological scales, the cumulative effect of molecular cloud collapse influences the history of the universe itself. The cosmic star formation rate rose gradually after the first galaxies formed, peaked billions of years later, and has been declining ever since. This rise and fall reflects not only the availability of gas, but the internal regulation imposed by molecular cloud physics. The universe did not light up all at once. It brightened slowly. This slow brightening shaped the thermal and ionization history of the universe. Radiation from stars reionized intergalactic gas over extended periods. Chemical enrichment spread gradually through cosmic structures. The universe transitioned from simplicity to complexity without sharp discontinuities. All of this traces back, in part, to the quiet way stars form. What makes this especially striking is that none of this requires fine-tuning or special conditions. The physics involved is simple: gravity, cooling, motion, and magnetism acting in cold gas. There are no thresholds that produce sudden global change. Instead, the universe runs on processes that dissipate energy gently and redistribute matter incrementally. This is what can be meant by the universe running on quiet physics. Most of its structure is not built through explosions or singular events, but through slow losses of energy, gradual rearrangements, and long-term balance. Molecular cloud collapse exemplifies this principle. It is one of the primary ways the universe converts diffuse matter into organized structure without ever drawing attention to itself. Even the most spectacular astrophysical phenomena rely on this quiet foundation. Massive stars, supernovae, and energetic feedback all depend on the prior existence of molecular clouds that collapsed slowly enough to allow structure to form. The loud events are consequences, not causes. They punctuate a process that is otherwise steady and subdued. In this sense, molecular clouds are not just sites of star formation, they are regulators of cosmic time. They determine how fast complexity unfolds. They set the tempo for galactic evolution, chemical enrichment, and planetary emergence. Their silence is not emptiness, but restraint. The universe could have been very different. With more efficient cooling or weaker support, clouds might collapse rapidly, producing a universe that burned brightly early and then faded. With stronger support or weaker cooling, collapse might be rare, producing a dark, underdeveloped cosmos. Instead, the balance achieved allows for sustained evolution over billions of years. That balance is not imposed by design. It emerges naturally from the interplay of forces in cold gas. Molecular cloud collapse is slow because it must be. If it were faster, the universe would exhaust itself. If it were slower, complexity would stall. The quiet pace is the only one that allows galaxies, stars, planets, and eventually observers to exist together in the same universe. Seen from this perspective, the collapse of molecular clouds is not a minor detail of astrophysics. It is one of the central processes that determines what kind of universe we inhabit. It shapes not only where stars form, but how long galaxies live, how chemistry evolves, and how complexity accumulates. The universe does not rush. It cools, condenses, fragments, and reorganizes itself patiently. Molecular clouds are where this patience is most clearly visible. They remind us that the dominant mode of cosmic creation is not explosion, but endurance. The collapse of a molecular cloud carries an unexpected philosophical weight precisely because of how little it resembles our intuitions about creation. Human stories of beginnings are often violent. Myths speak of battles, ruptures, divine commands, explosions of light. Even in modern science, our cultural imagination gravitates toward dramatic origins. The Big Bang as a flash, stars as blazing furnaces, galaxies colliding in fireworks of light. Against this backdrop, the silent collapse of a molecular cloud feels almost unsettling. Something fundamental is being created, and yet nothing announces it. Creation without violence challenges a deeply ingrained assumption that meaningful change must be loud, rapid, or disruptive. Molecular cloud collapse contradicts this assumption at every level. Matter reorganizes itself without shock, without rupture, without spectacle. Gravity does not tear the cloud apart. It persuades it inward. Energy is not released in a burst. It is quietly carried away photon by photon. The system becomes more structured not through upheaval, but through loss. This reframes creation as a subtractive process rather than an additive one. Nothing new is injected into the system. No external force intervenes. Instead, the cloud slowly sheds energy, and in doing so, allows gravity to express itself. Structure emerges because resistance fades, not because force increases. The star is born not from an act of violence, but from the gradual removal of obstacles. That idea runs counter to how humans experience causation. On human timescales, change is associated with action. We push, strike, ignite, build. We measure significance by visibility and immediacy. But molecular clouds operate on timescales so long that the very notion of an event loses meaning. There is no moment of collapse. There is no instant when the cloud becomes unstable. There is only a slow drift toward inevitability. The timescales involved stretch human intuition beyond its limits. Hundreds of thousands of years for a dense core to collapse. Millions of years for a cloud to assemble, fragment, and disperse. Tens of millions of years between the initial gathering of gas and the final ignition of stars. These durations are not merely long, they are qualitatively different from the scales on which human cognition evolved. We are creatures attuned to days, years, perhaps generations. Molecular cloud collapse unfolds across spans of time that erase the concept of urgency altogether. When processes operate on such timescales, violence becomes inefficient. Explosions are fast. Shocks are abrupt. They dissipate energy quickly and locally. But building enduring structure requires the opposite. It requires patience, dissipation, and continuity. The universe appears to prefer slow processes, not because they are gentler in any moral sense, but because they are effective at producing stable outcomes. This preference becomes evident when one steps back and surveys cosmic structure as a whole. Galaxies are not assembled by singular cataclysms, but by prolonged accretion and cooling. Disks form as gas radiates energy and settles. Dark matter halos grow through countless minor mergers rather than singular collisions. Even black holes, often portrayed as violent entities, grow primarily through steady accretion rather than dramatic events. Spectacular phenomena do exist, but they are punctuation, not grammar. Supernova, gamma-ray bursts, and mergers grab attention precisely because they are rare and brief. They dominate images and headlines, but they do not dominate mass, time, or structure. Most matter in the universe spends most of its existence doing something far quieter, cooling, drifting, orbiting, and slowly rearranging itself. The silent collapse of molecular clouds is therefore not an anomaly, it is representative. It reveals a deeper pattern. The universe constructs complexity through processes that minimize drama. Spectacle is not how structure is built, it is how structure occasionally releases excess energy. The loud moments are outlets, not engines. This realization shifts how one interprets the history of the universe. The narrative becomes less about explosive beginnings and more about sustained restraint. After the initial expansion, the universe did not rush toward complexity. It cooled. It waited. Matter spread thinly for hundreds of millions of years before the first stars formed. Those stars formed slowly, inefficiently, constrained by the same quiet physics governing molecular clouds today. The emergence of planets, chemistry, and life followed the same pattern. Complexity was delayed not by lack of possibility, but by the slow pace of prerequisite processes. Heavy elements had to accumulate gradually. Dust had to form and persist. Clouds had to collapse quietly many times before stable planetary systems could exist. Silence was not a background condition, it was a requirement. There is also a conceptual humility embedded in this process. Molecular cloud collapse does not privilege observers. It does not scale itself to human relevance. It unfolds whether or not anything is watching. The universe does not announce its creative acts. Most stars form in regions that will never be observed directly. Most collapses leave no trace discernible from across the galaxy. Creation is the default state, not a performance. This challenges the idea that importance correlates with visibility. In human affairs, what matters is often what is seen, recorded, and remembered. In cosmic evolution, what matters is what persists. Molecular cloud collapse matters because it sets conditions that endure for billions of years, not because it is observable in the moment. Silence, in this context, is not emptiness. It is efficiency. It is the absence of wasted energy. Violent processes dissipate energy rapidly and indiscriminately. Quiet processes channel energy loss in controlled ways, allowing matter to settle into ordered configurations. Silence is the sound of a system finding stability. This has implications beyond astrophysics. It suggests that the universe is fundamentally conservative with its energy. It prefers pathways that minimize excess motion and avoid unnecessary disruption. Gravity, when allowed to act in a cooling medium, does not rush. It shapes patiently. The structures it produces are robust precisely because they were not forced into existence abruptly. The idea that silence is a fundamental feature of cosmic evolution also reframes humanity's place within it. Life emerged not during violent epochs, but during long periods of relative calm. Planetary systems require stable environments. Biology requires continuity. Intelligence requires time. All of these are downstream consequences of a universe that builds slowly. If molecular clouds collapsed explosively, stars would form rapidly and destructively, planetary systems would be unstable, chemical enrichment would be erratic, life, if it arose at all, would face constant disruption. The quietness of collapse is therefore not incidental. It is foundational to the existence of observers capable of reflecting on it. This does not mean the universe is gentle in any sentimental sense. It is indifferent. Silence does not imply care. It implies that the governing laws favour dissipation over accumulation, gradual change over abrupt transformation. The universe does not avoid violence. It simply does not rely on it. From this perspective, the spectacular events that capture attention are exceptions carved out by extreme conditions. They occur when energy becomes trapped, when cooling fails, when balance is temporarily lost. Molecular clouds represent the opposite regime, open systems where energy escapes easily and balance is restored continuously. In such systems, collapse is not a crisis, it is a transition. The philosophical weight of a silent collapse lies in how it forces a re-evaluation of what it means for something to begin. Beginnings need not be marked by boundaries or signals. They can be extended processes without clear start or end. A star does not begin at the moment fusion ignites. It begins when a region of gas first becomes unable to resist gravity long before any light is produced. This challenges narrative thinking itself. Narratives seek moments, causes, climaxes. Molecular cloud collapse offers none. It is all middle, all continuation, all slow drift. The absence of a dramatic origin does not diminish significance. It redefines it. Silence also alters the emotional register of cosmic understanding. Awe is often associated with grandeur and power, but there is a different kind of awe in recognizing that the universe accomplishes its most important work quietly, that stars, planets, and ultimately life arise not from cosmic violence, but from patience, loss, and restraint. In the end, the silent collapse of a molecular cloud is not merely an astrophysical process. It is an example of a broader truth about how complexity arises in the universe. Structure forms not because energy is unleashed, but because it is allowed to leave. Time is not compressed into moments. It is stretched across epochs. Silence is not the absence of activity. It is the mode in which activity becomes lasting. The universe does not shout itself into existence. It cools, settles, and waits. And in that waiting, everything we recognize as structure slowly takes shape.